Okay, so we're going to revisit an old favourite, connected particles. Just to remind ourselves what that means, it's when we're talking about objects, modulus particles, which are connected in some way. So either by a string or a rod or some other connection, which means that when one moves, the other moves. The case that we'll be looking at for this lesson is going to be a string. And specifically, we're going to have two objects connected by a string wrapped around a pulley. And this is all going on an inclined plane. I've got a couple of examples and some questions after. And there's also a little bit of information relating to the force that's exerted on a pulley, but we'll come to that in a bit. Before we continue with examples then, what I'd like to do is to just sort of draw a kind of standard example. So let's switch to yellow. Let's say an inclined plane, and just sort of draw the kind of classic situation that you might have. So in this case, we've got an inclined plane. I'm going to draw a pulley at the top of the inclined plane, and then let's have some string which is wrapping around that pulley, and some objects kind of sitting, let's do blue objects, kind of sitting, these are our particles I suppose, and one's hanging here and the other is on the inclined plane. And maybe I'll close this off just to make that complete. Okay, so this is the classic kind of example of connected particles on an inclined plane, and we'll see two examples, but before we see those, what I'd like to do is think about all the forces involved in this case. I'll say the inclined plane is smooth, but what I want you to do is now draw this diagram and think, what are all the forces involved? Maybe label them according to what they are. So, I don't want to give anything away. Just label them according to what you think they are. You don't need to know the magnitudes of the forces, but what you do need to know is the direction and the type of force it is. So give that a go, see how many you can label, and then we'll look at it together. So you can pause the video now. Okay, so let's see what forces we can muster up. Let's look at this object here first. What forces we got on that one? You're going to have a weight. Don't know what it is. Let's call it W. It'll probably be some mass times G, but as a full unknown, we'll just say it's W. On the string, you've got multiple forces. So we've got the string exerts a tension on the object here. There's additionally tension around the pulley here, same tension, T. Tension here again, going out from the pulley, and additionally some tension here pulling this blue box up here. Okay. What else have we got? This box is also going to have a weight. In this case, potentially different to the weight of the other box. In general, we don't know if they're the same or not, so let's call them W1, W2. And is there anything missing? We've also got reaction force, so that's going to be perpendicular to the slope. So there's some sort of reaction force there. Okay. If there was friction, you might also have some friction going on, but in the case of a smooth slope, there's no friction. Okay. So these are the forces, and that's what we're going to mainly be working with. Now there is one more thing I'd like to talk about before we move on to the examples, and that's what's going on here with this pulley. In fact, let me just copy this over to the next slide. Okay. And the main thing I want to focus on is to just remind ourselves that when you've got a pulley and a string going around it, as long as the pulley is smooth, then we can say that these two tensions are the same. And it doesn't particularly matter what the angle of the string is or anything like that. So if I put up a few other examples, So let's say, you've got a string that's wrapping around like this, say, or you could have a string like this, or even in a more extreme case, something like this. It doesn't particularly matter. As long as the pulley is smooth, you're going to have tension, T, going along the string and away from the pulley, like this. Okay, so these are three separate cases I'm sort of drawing out here. So that's just to remind you that the tension of the string around a pulley, it looks like this. Okay. Cool. All right. So let's look at an example. So in this case, it looks just like what we've drawn, except we're told the masses. So we've got 5 kilograms, 10 kilograms. We're also told the angle alpha, pulley smooth. What else are we told? There is friction in this case. So unlike the previous diagram, we are also going to have to add in some friction. And the coefficient of friction we're told is 0.2. Okay. And then we're going to find the acceleration and the tension. So first off, let's see. Well, let's draw the diagram as it is. In fact, I'm going to make this slightly smaller. And I'll just copy it from over here actually, because that works out quite well. Okay, so that's the diagram. Makes sense. Let's just change a few bits that we now know about. So for example, this W1 and this W2, we've been specifically told this one's 10G because it's 10 kilograms. This one's 5G because it's 5 kilograms. We're also told that this is alpha. And we're told there's friction. Now let's just think for a moment. Which way is this thing naturally going to be moving? System is released from rest, find the acceleration of the system. So it seems to me, if you've got a 10 kilogram mass here and a 5 kilogram mass here, then quite naturally, when I let go of this 10 kilogram mass, it's going to be pulling this 5 kilogram one up the slope. And what that therefore means is that the friction is going to be acting opposite to that motion, will be going down the slope. So let's add in the friction here. Let's use a straight line. So we've got the friction. And do we know what that's going to be? Well, we know that mu is equal to 0.2. So therefore that friction there is going to be 0.2 times R. And we know that it's the maximum friction, 0.2 times R, which is F max, because the object's going to be moving. And if an object is moving or about to move, then the friction is maximal. Okay. Right, anything else we can note down? Tan alpha, let's sort this one out. Tan alpha equals 0.75, that's 3/4. Now remember the trick. You can always draw a triangle, right angled, and say if alpha's there and 3/4 is opposite over adjacent, then I've got 3 and 4 here, therefore this is 5, and you can then find the fact that sine alpha is equal to opposite over hypotenuse, 3/5, and cos alpha in this case is adjacent over hypotenuse. Okay, I think I've talked about this before, but I'm just running through it very quickly here. But you should be comfortable with doing something like that. If you're ever forgetting, you can always just do tan inverse of 3/4 and then just do sine of that number. You should get 3/5. But that's the faster way to do it there without using a calculator. Okay, so what else can we put on the diagram? I think that's it in terms of information. Okay, so we're going to need to find the acceleration of the system. Let's move this across actually so we have a bit more space. So if we want to find acceleration, we're going to have to think about forces. And here's the thing about connected particles to remember. Once I let go of this, so let's say I'm holding this blue object here, and once I let go, it's going to start falling down. And similarly, this blue object is going to start going up the slope. They're connected with the green string. Because they're connected, that means their motion is going to be the same, speed at least. Like the direction is different. This one's going vertically down, this one's going diagonally up. But their speed and also their acceleration is going to be the same. So what we're going to do is find the resultant force up the slope for that object, find the resultant force downwards for this object, and in each case use F equals ma. And the A, which is the acceleration, is going to be the same in both cases because they're connected. Okay, so let's see what that looks like. In the case of let's do this, the object here, the 10 to 10g one. So for that one, what is the force? We've got, let's take down as positive. Okay, and we'll have F is equal to 10g minus t, and that needs to be equal to ma, which in this case the mass is 10, and we just get a. Okay, so to conclude, we end up with 10g minus t equals 10a. Okay, and that's the bit of information that we've got for that object there. Okay, a is the thing we're trying to find, remember. I don't know what t is, but presumably it won't matter once we get a bit more information. Now with this one here, we're going to resolve up the plane. So we've got t going up, that's this one there. We've got minus 0.2 r going down. The r here we can ignore, it doesn't particularly matter, at least not at this stage. And what about the 5g? We need to split that up first, so let's do that now. So if I split that up, that's alpha. We've got 5g cos alpha. This should all be very familiar. 5g cos alpha, and this part here is 5g sine alpha. So now if I go back to what I was doing, which was resolving up the plane, we've got the t going up, 0.2r going down the plane. We've also got 5g sine alpha going down the plane, so let's take that away. And that is the F in this case. That's the net force. Okay. So that is going to be equal to ma, which in this case is equal to 5a. Okay. Let's just make note of that over here. So we've got t minus 0.2r minus 5g sine alpha, and that's equal to 5a. Okay, so let's take a note of that here, and I'll get rid of this little bit here. Okay, so these are two equations I've now got. Let's hide some working. The problem now is this r at the moment. So I don't know what that is yet, or do I? So if we look here, we've got r going up and out perpendicular to the plane, and we've got this 5g cos alpha going down, and that's it. That's the only thing that's going in that direction. So this r must be equal to this 5g cos alpha. Because the object's not coming off the plane, not going into the plane, they must be equal. The resultant force must be 0 in that direction. So r must be equal to 5g cos alpha. Therefore, so if r is equal to 5g cos alpha, I'm actually just going to go over here and replace that r with 5g cos alpha. Now 0.2 times 5, that's actually just 1, isn't it? So then 0.2 times 5g cos alpha is just going to give me g cos alpha. Great. And now let's substitute in these sine alphas and cos alphas that we worked out earlier. Cos alpha is 4/5, so g cos alpha becomes 4/5 g. And sine alpha is 3/5 times 5g gives me 3g. So that becomes minus 3g. And that's all equal to 5a. Okay, so now we've got two equations with two unknowns, t and a, right? G, we know what that is. So we should be able to solve. And now we've done most of the work for both a and b, right? Because we're being asked to find the acceleration and to find the tension. And that's what we're about to do. We just need to do a bit of rearranging. What I'd suggest is let's combine these 4/5 g and 3g. And actually, let's just work out the number. So if I get my calculator, I'm going to do minus 4/5 times g, minus a further 3 times g. I get minus 37.24. 37.24. And 10g, that's just 98. Okay. If I add those two together, the two equations, so let's do that plus this. So on the left-hand side, the t's are going to cancel. I'll get 98 minus 37.24. Work that out. You get 60.74. And that's going to be equal to 15a if I add together the two right-hand sides. And therefore, we get a is equal to 4.05, roughly speaking. Okay, that's my value for a. And t, let's see, t is going to be equal to 5a plus 37.24. So let's multiply that a by 5, add 37.24, and we get 57.49, roughly speaking. Is that the right answer? Yes, it is. So that's it. We've got our a and we've got our t. Okay, so just to recap, the method was, as always, draw a diagram, label all the forces, and then the trick was to consider the two objects separately. So we resolved the forces on this object in the direction that it's going to move and said that's equal to ma. Then we resolved the force for this object only in the direction it's going to move, which is up the plane, and said that's equal to ma for its specific m. And we've got two equations, both of them with the same value for a. Which we could then solve. And the only extra little bit we had to do was to say, well, this reaction force must be the same as this component of the weight here, 5g cos alpha. And that was able to get us to eliminate the r. Cool. Okay, so before we look at the next example, there's just one thing I'd like to mention. And that is very specifically, what is the force exerted on a pulley? And it's not quite what you think of it being as just these two tensions that we've looked at before. Okay, you might sometimes be asked by a question, what is the force exerted on a pulley? And to really understand what they mean by that, let's look in very fine detail what's going on with a pulley. So this blue circle here, I'm drawing it as a pulley, and let's say you've got a string coming in at some angle. Okay, it comes in at some angle and it sort of wraps around the pulley. So, you know, technically you've got the string going around like this, and it comes straight down. Okay, so this is the zoom in of the pulley. Oh. And as I said, you've got tension on both ends of the string. So in this case, you've got some tension going down here, say, and some tension going along here. Okay, so there's some tension there, and there's some tension there. Okay, now if you're asked what's the force exerted on a pulley, it's not T. What it's actually asking you for is what is the resultant of both of these two tension forces pulling on the pulley. So if you can kind of imagine you're the pulley, right? And you've got a force that's pulling you this way, and another force, same magnitude but different direction, pulling you that way. What are you actually going to experience as a total result? You're actually going to experience a force that's going like sort of this direction, kind of halfway between the two. Halfway between the two, and perhaps more than just T in total. Okay, and it's this force, this single force, that we're actually being asked for when we're asked to find the force exerted on a pulley. So now, to get into the maths of it, we need to go back to treating the pulley as just a single point. Okay, so let's go back and pretend the pulley is just a single, very small point. Okay, and the string, again, is coming up like this, let's say, and down like that. Okay. And let's say the angle, the angle of the pulley, sorry, the angle between the two strings, let's say it's theta. Okay. And we're going to use this to get our answer here. So we've got some tension on the string going this way, again, tension on the string going this way. So it's exactly the same diagram as before. I'm just using a tiny dot for a pulley now instead of a massive pulley. And what we want is the resultant of these two forces. Now, remember that geometrically, the resultant of two forces is the same thing as putting the forces head to tail. So let me just try and extract these two forces. So I'm going to take the red one going down and the red one going diagonally. Okay. And what happens if I put these together head to tail? I should get a resultant force. Okay, let's do the resultant force in yellow. So this line, that's actually my resultant force, and let's put that in place. Looks like that. This is what we actually want to find, that force there. Okay, and how big is that force? That's another question. Well, here's how we can answer that. Let's actually put these red vectors in place now. We can see how this all lines up, right? As a sort of parallelogram. So it's that yellow line. I want to know, how long is that yellow line? And you're given the following information. You're told that this is T, this is T. That's an angle theta. And then this is also the same length T, and this is the same length T. And also, these two lines are parallel, and these two lines are parallel. Can we find the length of that diagonal? Is there a way we can do that? Well, here's what we can do. Let's add in another line horizontally. Okay, so this is me just adding in a line. And what do we notice about the green line and the yellow line? Is that they are perpendicular. And then, instead of calling this theta, let's split it up. Let's halve it, in fact, and let's just call that little bit there, let's call that theta over 2, which makes sense because the yellow line has split it in half. If that's theta over 2, and this is t, what's the length of this bit of the yellow line? Just this bit there. It's going to be t times cos of theta over 2. Right, so just to be clear, I'm talking about this bit here, going from here all the way along to there. That's t times cos theta over 2. Okay, just using trig, where t is the hypotenuse. And therefore, by the same logic, this one here, I mean, it's the same length, because this green line has split it exactly in half. That part there is also t cos theta over 2. So therefore, we've almost come up with our formula. Tension on the pulley oh, sorry, not tension on the pulley. I need to be specific. Force exerted on the pulley. In fact, let's do it here. Force exerted on a pulley is 2 times t cos of theta over 2. Right, it's 2 because I'm adding that one to that one. Where theta is the angle between the string, is the angle between the two parts of the string. Okay, I mean, you could have been fine just sort of learning this, you know, 2t cos theta over 2, but you know, here is the explanation. Hopefully the explanation does make some sense to you. You might sometimes see it as, instead of theta over 2, they might just write theta, in which case theta has just been taken to be half of the angle between the two strings by default. But in my case, I've said theta is the angle between the full angle. So therefore in the formula it's theta over 2. It doesn't really matter as long as you're clear what you're talking about when you say theta. Okay, cool. All right. I did say there was going to be a second example, but I think actually, to be fair on you, I'm going to hold off. We'll save it for the next video, and instead we'll just give you some time to try some questions now. Okay. Okay, so have a go at this one. Fairly similar to the question that we were doing in the example, but this time you've got a few different things that you're trying to calculate, but still the same idea. You need to consider the two separate objects, the particles A and B. Try and consider them separately and think about the formulas that describe their movements separately, and use F equals ma. So give that a go. You can pause the video now. Okay, and let's take a look at the answers. There. Okay, and I think just one more question should be enough. It is quite a difficult topic. See how you do with this one. In this case, the particles are a trailer and I think a van, so but we're modelling them as particles. This time they're connected not by a string but by a tow bar. And the only difference between that really is that with a string, when you pull it, there's tension on each end, but when you push it, there's no tension. It just becomes slack, becomes floppy, and there's no tension. Whereas a tow bar, whether you push it or you pull it, it's not going to compress, it's not going to stretch. There's always tension in a tow bar. And the direction of the tension depends on if you're stretching it, you're pulling the tow bar, or if you're pushing it. Okay. So you really want to try and get the force diagram correct for this one first before you start trying to do your calculations. Right, you need any help with that, you let me know. Cool, alright, so give this one a go. Pause the video now. Okay, and there is your answer.